Recall that there is only one line perpendicular to a given line at a point on that line. Theorem 6.4.1. The line that is perpendicular to the radius of a circle at its endpoint on the circle is a tangent to the circle. Construction 8. To construct a tangent to a circle at a point on the circle. Plan. The strategy used in Construction 8 is based on Theorem 6.4.1. For Figure 6.55a, we will draw a radius extended beyond the circle. At the point on the circle, point X in Figure 6.55, we construct the line perpendicular to segment PX. The constructed line, line XW in Figure 6.55c, is tangent to circle P at point X. Given circle P with point X on the circle, see Figure 6.55a. Construct a tangent, line XW, to circle P at point X. Construction. Figure 6.55a. Consider circle P and point X on circle P. Figure 6.55b. Draw a radius, segment PX, and extend it to form ray PX. Using X as the center and any radius length less than length XP, draw two arcs to intersect at points Y and Z on ray PX. Construction. Figure 6.55c. Complete the construction of the perpendicular line to ray PX at point X. From point Y and point Z, mark arcs with equal radii of length greater than length XY. Calling the point of intersection point W, we draw line XW, the desired tangent to circle P at point X. Construction number 9. To construct a tangent to a circle from an external point. Given circle Q and external point E, see Figure 6.56a. Construct a tangent line segment ET to circle Q with T as the point of tangency. Construction. Figure 6.56a. Consider circle Q and external point E. Figure 6.56b. Draw a line segment EQ. Construct the perpendicular bisector of segment EQ to intersect segment EQ at its midpoint M. Construction. Figure 6.56c. With point M as center and length MQ, or length ME, as the length of radius, construct a circle. The points of intersection of circle M with circle Q are designated by point T and point V. Now draw segment ET, the desired tangent. In the preceding construction, segment QT, not shown, is a radius of the smaller circle Q. In the larger circle M, angle ETQ is an inscribed angle that intercepts a semicircle. Thus, angle ETQ is a right angle, and segment ET is perpendicular to segment TQ. Because the line drawn perpendicular to the radius of a circle at its endpoint on the circle is a tangent to the circle, segment ET is a tangent to circle Q. The remaining theorems in this section involve inequalities in the circle. Theorem 6.4.2. In a circle, or in congruent circles, containing two unequal central angles, the larger angle corresponds to the larger intercepted arc. The converse of Theorem 6.4.2 follows, and it is also easily proved. Theorem 6.4.3. In a circle, or in congruent circles, containing two unequal arcs, the larger arc corresponds to the larger central angle. Given, in Figure 6.58, circle Q with the measure of arc RS greater than the measure of arc TV. A. Using Theorem 6.4.3, what conclusion can you draw regarding the measures of angle RQS and angle TQV? Solution. Measure of angle RQS is greater than the measure of angle TQV. B. What does intuition suggest regarding the length RS and the length TV? Solution. Length RS is greater than length TV. Theorem 6.4.4. In a circle, or in congruent circles, containing two unequal chords, the shorter chord is at the greater distance from the center of the circle. Theorem 6.4.5. In a circle or incongruent circles containing two unequal chords, the chord near the center of the circle has the greater length. Theorem 6.4.6. In a circle or incongruent circles containing two unequal chords, the longer chord corresponds to the greater minor arc. If length AB is greater than length CD in figure 6.61, then the measure of arc AB is greater than the measure of arc CD. Theorem 6.4.7. In a circle or incongruent circles containing two unequal minor arcs, the greater minor arc corresponds to the longer of the chords related to these arcs.